Okay, so in our first two examples, we graphed a single linear inequality. So now we're going to extend that to graphing systems of linear inequalities. So two or more linear inequalities combined at the same time. A feasible set, denoted with a capital S, is the set of all points that satisfy the inequalities, which are also sometimes called the constraints in a system. So we're going to basically graph each inequality and we're going to determine the region that they have in common. So we're looking for the overlap. If your feasible set is bounded, basically if you can enclose it by a circle, otherwise we would call it unbounded. This first example, we've already done each of the individual inequalities together. So we're just going to combine up what we had for those. So that first one had intercepts of, turn back on my pen, -2, 0, and 0, -2. The second one, which I'm going to do in red this time, had intercepts of 0, -6, and 2, 0. Okay, so whenever I'm going to just get these back on my graphs. So I had the -2 and the solid line. And then the other one we had these 2 points and another solid line. Using colored pencils or something like that can really be helpful when you're doing these systems because you can really see that overlap happen. So again, stealing from our prior problem, we had everything. Actually, I'm going to scroll back up so we can see it. We had everything on the top part of the first line and then on like the left-hand side of the second line. So I'm going to use the color coding to do that. Everything on the top of the blue line was shaded, and then everything on the left of the other line was shaded. And what I can see then is that my answer, and I'm going to color code it purple for the intersection of red and blue, is this area right here. This is the area that satisfies both inequalities. All the points in this area satisfy each one of those. And so that is our final solution. This one, I cannot draw a circle around it, right? I can't enclose it into a circle because these are going to just keep going out forever in this direction. So this one would be considered unbounded. Okay, let's do another one from scratch this time, and this one's got a little bit more going on. It's got several other inequalities. These first couple, I'm going to look at what my intercepts are. So I'm going to just sort of think these through and save a little bit of writing. If I put a 0 in for the x, if I put a 0 in here, then I'm going to get a -4 for the y. And if I put a 0 in here, I'm going to get a +3 for the x. Okay. I'm also going to look at the intercepts of this one. If I put a 0 in for x, then 2 times 5 gives me 10, so 5 for the y. And if I put a 0 here for the y, 5 times 2 gives me 10, so for the x it's going to be a 2, 0. The other ones are either horizontal or vertical lines, so I don't really need to find the intercepts. I just have to remember how to graph those types of lines. So first, I'm going to also notice all of these are non-strict inequalities, so we haven't seen any examples with dashed lines. They certainly exist. These just all happen to not be from random examples that I pulled. So this first one, I'm going to graph 0, -4, and 3, 0, and a solid line through there. And then I'm going to graph 0, 5, and 2, 0. And we need another solid line through there. And then I have some other lines on here, which I'm going to just go ahead and mark off in black and hope we can see those good enough. We have x is greater than or equal to 0. Actually, so maybe I'm going to use a different color. I don't want to use that. I'm going to use this burnt orange color. So x equals 0, if x equals 0, I'm right here, and the line where every point has an x-coordinate of 0 is actually this y-axis. This is the x equals 0 line. Y equals 0 is actually the horizontal axis, and you can do all of these in different colors if you want. So this is the line y equals 0. And the last one that we have is y equaling 7. So I would need to go up to the y equals 7. So this was 5, so y equals 7 is right here. And the line with all y coordinates being 7 is right here. So we have quite a lot going on here. We need to do some test points for these top two. So I'm going to go back and grab my blue. So a test point for this one, we can test 0, 0. It's available. So if I put in 0 and 0, does this come out true or false? 0 is less than or equal to 12 comes out true. So as far as my blue line is concerned, I want to shade the side that has 0, 0 in it, which is right here. So I can shade, I know already that it's not in some of these bottom regions, right? So I've already narrowed it down a little bit to what my final answer is going to be. Let me grab my red. Let's test this one. So if we put in 0, 0 there, which we can do yet again, that line doesn't have 0, 0 on it. Oops, greater than, or equal to 10. Is 0 greater than or equal to 10? No. So as far as this red line is concerned, if you come and look at this line, do not shade the side over here that has 0, 0 on it. Shade the other side. So in this case, we're going to shade upwards. So again, we've sort of got we know it's kind of up here somewhere, but we still have lots of regions to consider here. We only want to keep the side where the x's are greater than 0, so this direction. So we've knocked out a little bit more options. We only want to keep the area where the y's are greater than 0, so only up from this line. And it gets a little messy here. Finally, we want to keep where the y's are also less than 7, so below this line. So can you go through and figure out where is it in here that got shaded by every single one of these? And you have to be very careful because I can't go past this line as I'm shading because on the left-hand side of this y-axis, I can't keep that. So there's like this little triangle off to the left I can't keep. And I have to stay on top of this red line and to the left of this blue line and under this pink one. So I'm really trapped. Oops, I need to delete that a little bit. I can't shade here. That part went under that blue line. So that's no good. Get that drawn back on there. Okay, I can't go on the other side of it. So I'm trapped right inside here. Oh, and again, I messed up a little bit. I need to erase. I can't dip below that line right there. I can't dip below that y equals 0 line. So I'm boxed in there. I'm going to try to make this look really nice. You will have a little bit of an easier time because you will be for the most part, choosing multiple choice. So getting that drawn perfectly, you won't have to be necessarily doing on the computer. You'll want to do it for yourself on your paper, but you'll want to be picking them. So look for those things though. Look for ones that may be trying to trick you where they've dipped a little below a certain axis or a little to the left or right of something when they shouldn't have been there. But that is our feasible region. This one can actually be enclosed by a circle, right? I could, if I wanted to, I could draw a circle all the way around that. So this one is considered bounded. While we're here, let's look at this next question. It says, refer to these solutions. Is the point 3, 3 a solution in system 1A? So in system 1A, let's find the point 3, 3. So the point over 3 and up 3 lands right on this line. It's a line that is enclosing our answer, our feasible region, and because the line is solid, the answer here would be yes. It's on the line that encloses that feasible region. What about for this next one? It says, is 0, 3? So 0, 1, 2, 3 is right here. Is that a solution here? Well, it's not, because it is not touching, it's not bounding that feasible region, it's not inside of it. So in this case, we would say no.